a physics-informed heterogeneous graph transformer for modeling big data in urban construction projects, after by Olga Solovey, Tatiana Goncharenko, Kyiv National University of Construction and Architecture. The increasing complexity of the construction project leads to generation of a heterogeneous data. This data is sourced or produced by used the Internet of Things sensor, the system that use the BIM models, and the data that it produced as a result of inspection and monitoring of the building project. Recent research in graph neural networks and graph transformers have demonstrated potential in modeling complex relation data structures. In particular, heterogeneous graph neural networks enable the presentation of BIM data as multi-type graphs where nodes correspond to building components and edges encode structural, functional, and spatial relations. Such approach allow capture high-order dependency and conceptual interaction within the building system. Despite this advantage, existing approaches remain limited in several critical aspects. Most models are poorly data-driven and do not incorporate physical-based knowledge, such as structural mechanics, material degradation, environment impact. And the BIM data and the Internet of Things data from sensors streams are treated in isolation, which do not allow to capture real-time impact on the BIM model. To address those limitations, the current research proposes a new framework to integrate heterogeneous data transformer architecture for modeling complex relation structure for BIM data, physics-informed features, and the impact from the environment. The goal of this research is to develop a physics-informed heterogeneous graph-based approach as a core component of a hybrid information technology for managing heterogeneous big data in urban construction projects, enabling prediction of the technical conditions and expectation need for structural elements. To achieve this goal, we set and resolve objectives. We develop physical informed heterogeneous graph transformer models that integrate domain-specific physical knowledge in the graph neural network architecture through the physics-based features and regularization mechanism to develop a training and validation methodology to verify the proposed model, and they provide the experiments to validate the approach. Heterogeneous graph definition consists of nodes, edges, and each node has its physical feature vector, which include three groups. It's a geometric characteristic derived from the BIM model. It's a degradation-related parameters derived from the physical model, and then the physics-informed indicator regarding the state of the structural elements. The scope for this research includes structural elements such as column, beam, slab, and wall. For the concrete column, the feature vector includes parameter, a safe factor of the column, time-dependent loss of rebuild radius, corrosion current density, and concrete cover thickness. And inspection is triggered if a safety factor drops below the critical threshold, which is set to 5.5, or if the rebuild radius more than 30% of the concrete cover thickness. All thresholds which are used in current research were sourced from official documents for the corresponding structural element. Uh, for beams, the physical feature vector includes parameters such as the initial and final crack length, the stress intensity factor, the fracture shortness of the materials, the bending stress, the yield stress, and the inspection is triggered if final crack length grows larger than a threshold, or if the beam overall safety factor drops below critical value, which is 2.0, or if the stress intensity factor at the crack tip exceed 85% of the material fracture shortness, or if the bending stress in the beam exceed 80% of the material yield stress, or if the final crack length has more than a triple compared to initial size. For the slab, the physical vector includes parameters such as stress and reinforcement, water leakage index, crack width, nominal yield stress of the steel reinforcement, critical threshold value for the water leakage index, corrosion penetration depth, thickness of the concrete cover, settlement introduce deformation. The inspection is needed if the steel reinforcements exceed 90% of the yield stress, or if the water linkage index exceeds a threshold of 0.5, or if the width of crack on the slab surface is greater than 0.5, or if the corrosion penetration depth has exceeded 70% of the protective concrete cover thickness, or if this settlement induce deformation or deflection of the slab is greater than 25 millimeters. For the wall, the physical feature vector includes parameters such as loss of energy efficiency, moisture index, sealant condition index, maintenance urgency index, predicted time to failure. And the inspection in flag is triggered if the predicted time to failure is less than 1 year, if the loss of the energy efficiency through the wall exceeds a threshold of 25 units, if the moisture index inside the wall structures surpasses a critical value, if the calculated maintenance urgency index exceeds a score of 8.5. The architecture of the physical form heterogeneous graph transform model starts with the point where each node in the graph starts with its basic feature. Based on attention mechanism, model identify which of the neighbors has the most important information for the current node. Three key vectors are calculated, such as query key at value. Then the query vector of the current node is compared with the key vector of the neighbors. The better the match, the higher the attention score. The score are normalized across all neighbors using the soft max function. For each neighbors, a message is created by multiplying its value by the attention score, and the target node aggregates all those weighted messages from the neighbors. This creates a new updated representation of each node that is enriched with information from the neighbors. After aggregated messages, the node state is updated using the neural network layer, including a residual connection to improve the training stability. And under node representation, finally the latest node is passed to the prediction layer to predict the probability of the need for the inspection. The loss function includes is a hybrid one, right? It consists of two terms. The first term is the cross entropy loss function that actually measure how well model predicts, and the second is a physical loss function, a regularization term that directly compare the model output to the physical base feature vector, which we define, and basically penalize right the model if the prediction not close to the physical plausible result. This methodology that we use to train the model includes the block forward propagation, prediction, and criticality evaluation, loss function computation, back propagation with updated parameters. During this shown on this slide, the uh, entropy-based uncertainty is calculated for each prediction, and critical score uh, is defined as a sum of three terms. Is it the physical state of the node? It's the prediction of the model and the model uncertainty associated with the prediction. The methodology we use to validate the model includes the the ability of the model are evaluated by analyzing the dynamic of the accuracy function over the training epoch. The model demonstrates a stable convert if the absolute difference between accuracy on the training set and accuracy on valuation set is less than set threshold. We use 5% threshold between training and validation performance on the accuracy curve. The model's prediction performance is quantified using the accuracy, and we said that it must be higher or equal to 90%. And then the discriminative capability of the model, so basically the model ability to distinguish correctly distinguish the structural elements in the data set is evaluated using the area under curves, and threshold that we use is 80% per each nodes. Then the model is performance of the model is verified using F1 score, which is considered to be equal or higher than 80% to prove that the model actually has sufficient performance. Then alignment between model prediction and physics-based indicator is evaluated using the mean absolute error. And finally, the validation of how close the model captures physical meaningful degradation compared to the physics-based indicators that we have is calculated using the Spearman rank correlation coefficient, which is said to be higher than 70%. The experimental setup includes a construction of the heterogeneous graph from the beam models, generation of physics-informed synthetic dataset, and configuration of training parameters. The first task here, the construction of heterogeneous graph was made from the EFS file of a beam model using the method we propose and verify in other research method for creating graph based on the beam model for predictive monitoring and buildings. And the heterogeneous graph transforming model was trained and evaluated on the synthetic dataset generated based on the beam model. The physical behavior of constructed element was modeled according to methodology we propose in the work physical state model of the structural elements for predicting building reliability using graph neural network. The data set is split into training, validation, and test subset. The heterogeneous graph transformer model is trained with a configuration which includes four heads, three message passing layer. A maximum number of epoch is set to 100. Model was developed in the Python programming languages using the PyTorch library, NumPy, Pandas, Sklearn, and Matplotlib. The results on the current slide is visualize the both loss curves, training loss and validation loss, steadily decrease, reaching a value of approximately 0.7 and 0.61 in the final epoch. The training was stopped according to early stop criteria as validation loss curve stopped improving after epoch number 76. The accuracy occurs on the right picture increases synchronously and remain close to each other. In the final epoch, the absolute difference between the scores was less than acceptance criteria, which was set 5%, 0.5%. The absence of significant gaps between the training and validation accuracy curves indicates the good generalization ability of the model. This slide presents the area under row curves we receive for each structural element. As seen for the beam, columns, and wall, the area under occurs close to 1, and for slabs, it is 84%, which is higher than set acceptance criteria 80%. The classification metrics. The overall accuracy of the model on the test data set, which includes 6,828 elements, is 92%, which satisfies our acceptance criteria 90%. And for beam class, the all classification matrix is close to 1. The confusion matrix confirms that all 171 beams elements were classified correctly. For wall class, the F1 score has value 98%, achieved due to nearly perfect precision and high recall. The model error for this class, false negative and false positive, is equal to 2.7% and 3.8% respectively. With the slab class is the most challenging for this model. F1 score is 85%. The main issue is related to low recall, as seen in the confusion matrix. 269 slabs, which is the 20% from all numbers, were incorrectly missed. At the same time, precision remained high. It's higher than 88%, meaning that elements classified as slab are most correctly. For the column class, the model achieved perfect recall, meaning it successfully found all 24 columns in the test set. However, there was at the cost of low precision, as the model incorrectly classifies 37 other elements as columns. F1 scores satisfy our set criteria 80% for all nodes except for the rail class column. However, given that for column we achieve the high recall, so all those elements are identified, this deviation is considered acceptable in our research. On the slides is presented how the model forecast of the critical score is actually impacting the graph state. On the left part, at the initial stage, where there was 60 days from the beginning, heterogeneous graph transform model attention is mainly based on the input feature nodes vector with a minimal influence from the neighbors. 18 out of 21 elements are marked in green, meaning that the condition do not require any inspection. And on the right slide, right picture, we illustrated the dynamic of the score when time was almost 2 years. And here is seen that the nodes are marked by yellow, meaning that the condition needs inspection and that was noted as a deteriorate. Critical score greater than 0.8% for two slabs at the very beginning moment at the 60 days is considered with the quantified metric is considered due to this low recall of the model for the column elements, sorry, for the slab elements. And that's why the model uncertainty is high for those elements, and we see that these elements are marked by the red color. In the conclusion, this study proposed a physics-informed heterogeneous graph transform model as a core component of our hybrid information technology for managing big data in urban construction project, enabling prediction of the technical condition and inspection need of the structural elements. The result obtained confirms that all key validation criteria are satisfied under the construction experimental condition. The proposed model novelty is was developed the physics-informed graph learning paradigm for the construction system. The practical significance of the proposed approach is its ability to support predictive maintenance of inspection planning uh, and as a result optimization of the resource allocation in urban construction project and enhance safety. Thank you for your attention.